Hello and welcome back to Granbury Volunteer Fire Department's online fire academy. I am Matt Hohan, training of operations, and today we're going to be covering building construction, section 22. Now, if you guys haven't looked ahead already, you're going to see that this is a very large section. We're going to have two presentations for you. This one on building construction, and then following this is going to be the art of reading smoke and building construction. The two of them combined really complement each other and really do round off a good junior firefighter coming straight out of an academy. Do be aware that building construction is one of those things that if you don't know it well, it's going to put you in a very bad spot. And that spot could get you killed. So you need to pay really good attention to building construction. Now, I'm not a big fan of going in and just telling me every single part of that building and what it does. What I want you to be able to recognize is how does the load of that structure move throughout that structure? How does an actual fire inside that structure physically affect that structure? And then lastly, how does the firefighting activities on scene in the extinguishment of that fire affect that structure? These are the things that we're going to focus on. Building construction's a massive topic. We're barely going to scratch the tip of the iceberg, and there's a ton to know here. I highly recommend that you find other classes that are a lot more detail after our academy to really build your building construction knowledge. Past that, anything else, make sure you write it down. Settle in. This is a long one. Describe the relationship of building construction to fire behavior. Guys, what we're going to look at here is a couple of different types of loads that buildings encounter, and these are under normal conditions. At the end of the day, our concern with building construction is what's happening to the building as it's burning, and the materials that are being consumed is part of the structure in the inevitable collapse. That's what we're really after here. Identifying the types of loads placed on a structure. So below we've got two great pictures, and one's for wind loads, one is for dead loading, example is snow. Then we have live loads, the physical people and the objects and materials inside the structure. And then you also have hydrostatic pressure from the subfloor that's below the ground level. So basically the pressure of the dirt and water pushing in on basement walls, and then ultimately the dead load of the complete building sitting on the ground. Now, another thing to consider is just the way gravity physically runs through the structure. And we're going to look at the picture on the right for this. And you can see a cross-section of a house, and we have gravity that's pulling down. And as the gravity is pulling the roof down, you can see the load is transferred to the peak of the house and then down through a main beam to the floor, where there is a cross section and just a header board, and the weight is then transferred diagonally across to another either pier or stud or whatever beam, and then ultimately down to the slab and through the ground. Now, identifying loads as to the direction in which they are placed on the structures. This is something that we have to pay attention to as we're doing an interior fire attack. What if the building holds a lot of water? Will the building be able to just hold the extra weight of water being added to the structure? What sort of pressure does the water put on the floor, but what about the walls? Another thing to consider with the loading of the building is as you start having to do forced entry or vertical ventilation, and you start tearing out wall studs and you start cutting holes in roof rafters, Where does the spread of the weight go? Obviously, that piece has been removed. Now, I can tell you right now that you can go in and remove one or two studs or one or two roof rafters as that building is standing. But if that building's already compromised, it's already losing the integrity of the building materials, and you go in and start removing supporting members, that building has a potential to collapse on top of you or right underneath you. Describe the effects of loads on various materials. This is a really big one. Certain materials are not created equal in this discussion. Things like steel and concrete are very strong, but concrete can take a lot of weight and a lot of heat, whereas steel can take a lot of weight, but you start adding any sort of heat to it and it'll turn to spaghetti in a few hundred degrees. Let's go to something like wood. It's not nearly as strong as steel, but a large wooden timber can burn for a long time because it's so dense. That piece of wood will be able to hold up longer than a piece of steel in a really hot fire. Then we get to other building materials like brick and stucco and hayed out blocks, and each of these materials is going to handle different. I know that this is an introductory class on building construction, but you also have to start your journey of building your own knowledge base on these materials, how they handle under loading, and how they handle under the loading of fire conditions. Lastly, identifying terms associated with building construction. You're going to start hearing a lot of those terms throughout this slideshow. By the end of this slideshow, you should have a lot of questions, and realistically, you should be looking into these questions yourself and then take them back to your home departments and start there. One thing that I wanted to add here, and with this slide, the load path of a building, and we're going to look at our little diagram here in a second. Don't forget that every single part of a structure is physically under a load, and the load may not be intentionally given as you start removing material for support, and then that load is going to very easily shift and compromise the rest of the structure. And a really good example of this is shear or lateral loads. Best place to encounter this is in an earthquake zone. Walls are built to take gravity weight and then the weight of the physical structure on top of them. So they're very strong standing up. But walls are very weak laterally. Any side impact, side force is going to significantly create a structure problem to the physical object. And what we're after here is the consideration of the forces when they're applied. So if we look at our picture here, we've just got a nice simple square building, okay, with a flat roof, and the gravity load is down. Now that roof structure is built with gravity in mind, and that roof structure goes across to our four columns, and the columns are what support the roof up and take the weight and transfer it into the ground. The beams are the unsupported part of the roof that run horizontally, and they also absorb a lot of the weight that's coming from the roof. So if we compromise this flat roof right here in the middle of a beam, let's say we just cut it in half, what is the integrity of that flat roof now? This is a system that's entirely built on rigidity within itself. It's a very strong structure. The second you take one of the equations out of the structure, whether it be a beam or a column, the structure's compromised. There's nothing you can do about that. And what I want you to do is take this into your firefighting. When you see major beams and major columns being threatened or compromised or already compromised or already diminished, that's a huge red flag. Interior operations stop. We're not progressing inside anymore. It's a defensive fire. You've got to back out. The whole structure is now threatening to come down. And it's just one part of the structure that's been threatened, but the entire integrity of the structure is now compromised. Now, before we bail off too deep into different types of building construction, we want to talk about the characteristics. And there's 5 types of building construction. Type 1 is fire resistive, and that's typically going to be your high-rise structures made of steel and fire resistive concrete. Type 2 is a non-combustible or limited combustible. This is going to be your big factory buildings, your big warehouses, your big grocery stores, and hospitals. It's going to be hayed-out block construction. It's going to be heavy metal construction. It's going to be just straight metal and heavy masonry or block construction. Type 3 construction is very common in our area. That's typically what we see all of our strip malls made out of in this area. It's a combination of wood and plywood and particle boards, and then the roof is typically going to have some type of metal truss system, typically seen in like a strip mall with a flat roof. Type 4 construction is very rare in this area. You do see it typically in churches and in banks, and that's where you see big heavy timbers running across the ceilings, a big log cabin, anything with that, just big giant wood support. Type 5 construction is just a straight up wood construction. Typical wood house, typical barn that's made on the side. It's just straight up wood construction. Describe various structural elements in building construction. Identify foundation assemblies, foundation walls, floor assemblies, ceilings and ceiling assemblies, various types of wall construction, roof types, roof coverings, and roof supports. Guys, if I went through this entire slide, just this one slide, this is a half a day project. You guys are going to have to do your own homework and your own research. Now, what we're going to go through is over here on the right slide. If you look at our slide, we're going to look at a very basic structure. Okay, simple type 5 construction, wood construction, and we're just going to go through and we're going to look at this structure as a whole. Okay, and we're going to start at the very bottom. That's the foundation. Okay, and then from the foundation, as we build up, the first thing we're going to put in is footings, okay? And that's what all the wall studs and what all the columns are going to physically attach to. From the footings, we go up, and that's where the wall studs come in. Now, a wall stud in the middle of a building is not going to be the same as a wall stud on a corner. Again, we're going to think of corner studs as columns. Those are critical points of a structure. There's a ton of weight of the structure running through there. Not only the building itself, but think about the roof. And if you have a 4-sided building and you just jerk out one of the corners of that building, how much weight's now just sitting down on that corner? And then on the opposite side of that, think of what, with all that weight sagging on that corner, what's happening to all the fasteners on the other end of the building, the opposite corner? It's trying to pull up. It wants to balance itself out. So it starts telling itself apart. Now, as we go up from the studs, we go to our very first beam. And that beam is typically called a header board or something of that fact. Okay, from the header, now we go into the actual attic and roof space where we're going to have our ceiling joists and then ultimately our rafters. And then ultimately, as we get to the very top of the building, the peak. The top beam, the tie beam, that's the peak. The edge of the roof is called the eaves, and as you progress through this class, you're going to see a lot of terms that are one-time use terms for the slideshow, but it doesn't mean they're not important. And I really recommend that you invest some time in identifying the different types of construction and their names, and then more importantly, look at it from this. If that piece is burned through, is the structure compromised? Now, identifying potential hidden spaces and structural elements that would allow for communication of fire and smoke. Not really sure what they're after here for communication, but what they're really talking about is the void spaces. Your typical void spaces in a house is going to be anything under a floor, anything behind a wall, and anything over the ceiling. So attic spaces, walls, and subfloor. That's where you're going to be finding any hidden fire and smoke. And then if they're an open space, realize that that smoke is how the fire physically moves throughout a structure. So if you have a fire in the subfloor and an open wall void, and that smoke is running to the attic, guess where the fire is going to run to really quickly? It's going to be the attic. I want to look at roof construction in just a little more detail. Here we have a slide with a whole bunch of just numbers and arrows, just giving you an idea of what some different stuff's named. But what I want you to really consider is the physical weight that's on top of a roof, and then good and safe places to actually vent a roof at. When we're venting a roof, we don't ever want to cut through the peak. We don't ever want to cut through the tie-in beam. We never want to cut that. Just the same as we would never cut through a column, we don't want to be cutting through beams either. We want to be cutting through the support facets of the structure. And in this particular case, that's going to be our joists and our rafters. We're okay to cut those. What I want you to look at, though, is I want you to look at the right side of the slide at number 8, and that's a collar beam. Okay, and if you see that collar beam, what it does is it not only helps tie the rafters and the joists together, but it also ties it into the peak. That collar beam is another piece of building material that we would never cut. We would not compromise that. So as you're doing your overhaul and your mop up and you're searching for hidden fires, or you're trying to create a vent point, we don't go in and start cutting away at support structures, support columns and beams of the structure. We can go ahead and look at and consider removing supporting parts of the structure in the sense of rafters and joists and studs, but we're never going after columns or beams. Identify the various building services for movement of people throughout a structure, elevators and stairways. Elevators are a firefighter's worst enemy when you're dealing with a large commercial or large residential structure. Particularly in Granbury, we have a lot of nursing home and assisted living areas, and your elderly population, they're not going to want to hump it up and down the stairs. So at least when you have a working fire at one of these facilities, you've also still got to deal with an elevator rescue. And one thing I want you to consider with an elevator rescue is it's this giant open shaft that runs throughout the building. It's a fantastic vent point. A lot of smoke's going to run to an elevator shaft, and that's how the smoke itself is going to exit the structure, and a lot of air is going to rush in through the elevator shafts. Now, stairways, here in Texas, most of our homes we deal with are Texas ranch style homes, and we have very few stairways to deal with. I can tell you this, in the event that you ever have to deal with working, particularly a basement fire or even a bad second story fire, stairways are chimneys. You really don't want to be making an advanced interior attack by progressing through the stairs, particularly down in a basement. You've got to get that basement vented, and you have got to get a water source on that fire and that atmosphere to start cooling it early, long before you ever consider making an attack down basement stairs. Again, I want you to think of it as a basement as a firebox, and you're going right up, make an entry right through the chimney. Now, mechanical operations of a building: heating, ventilation, air conditioning systems, utility chases, and vertical shafts. These are all points of ventilation for a structure, particularly the air conditioning and heating systems. Here in Texas, the vast majority of places are all heated and cooled with just an air conditioner and a heat pump. Well, that's great for us because it's all located in one spot. The problem is that those ventilation ducts move smoke very easily, but they also melt at a low temperature, so it allows for easy ventilation of the structure in itself. We don't have too many utility chases in the area, and when you do encounter a utility chase in this area, it's always going to be down. It's going to be in a basement, and those are typically very bad fires again. Emergency accessibility in buildings: windowless walls, access panels, roof hatches, smoke and heat vents, and skylights. These types of structures are typically larger. Think of Home Depots, Lowe's, and Walmart. From there, how many windowless walls do you ever see in residential? Well, you don't, but it's very common in H-E-B, Kroger, Lowe's, Walmart. Now, access panels, that's always going to be on the roof, and it's a metal ladder that's either on the outside or potentially on the inside of the building. And then the roof hatches is what's attached also with the access panels. And then smoke and heat vents are always going to be found on larger structures, and they're usually connected to the fire detection system. And if heat sensors are tripped and the smoke sensors are tripped, what you'll see is those heat vents will open up. And then lastly, skylights. And you guys know what skylights are. Identify door and window assemblies. I know I've covered doors and windows in great detail in previous slides. One thing I really want to talk about here is fire doors and their methods of operations. Fire doors are typically found in any structure that's going to be high occupancy. So schools, hospitals, occasionally churches, nursing homes, assisted living facilities, anything that's high residential, high occupancy. So the way these fire doors work is that in the event that the fire alarm goes off, the magnetic locks that hold the doors open will release and the door closes. The purpose of the door closing is to minimize airflow and to isolate smoke into an area, to ease in the evacuation of the structure. Once you've cleared the structure and identified that the fire is either out or non-existent, the only way to get the door to stay open again and reattach to the magnetic locks is to reset the fire alarm and have the panel cleared. Once that happens, the doors will go back to normal operation. If you have any questions on fire doors or more questions about windows and door construction, by all means bring it to class and we'll discuss it. Identify signs of potential collapse of a structure. This is the whole purpose of the building construction class for us. At the end of the day, that's great that we may know all the names of 500 different facets of a structure, but at the end of the day, the only reason that we really know this is so that we can identify how the fire is going to move through the structure, and then ultimately the signs of potential collapse. Let's look at our picture here on the right side of the slide. Fire through the roof. When you have fire through the roof, how did the fire get through the roof? Well, it had to burn away the roof. Is the structure now compromised? No, it's just being threatened. What are the other signs? Is the building leaning? Are the walls leaning? Do you see studs or rafters missing? How much of the roof is actually burning through? Okay. Is there cracks in the wall? And it doesn't just have to be brick or concrete to have a crack in the wall. I've seen a lot of wood houses with regular siding that you can see a very visible crack where the siding's starting to tear away. That's an obvious potential structure collapse. Smoke ejecting from mortars or other cracks in the wall. The mortar in between the bricks itself is physically being threatened. Now, down here at the bottom right, it says ornamental metal stars. And the best place you can see one of these is go down to the square, and you'll see that at the tops of the buildings, you'll see occasionally some of those buildings have big metal stars on the outside, and other buildings, they might just have what looks like a big metal plate. And the ones with the big metal plate, you'll see that there's a bolt and cable attached to it. That's in place because the structure's already showing signs of potentially collapsing, and those cables and the bracings put in to help tie the structure back together and help it hold itself up. So if you have a structure inside, what's happening to those metal cables that are helping support the outside walls from collapsing? Huge sign. If you see that, and you see that on a structure, it's a do not enter structure. Okay? There's 100 different signs that you need to be aware of for potential structure collapse. Not only is firefighters physically removing columns and beams, but then you have the fire and the damage that it's doing to the internal structure. And then ultimately, that building's not just going to fall down in the blink of an eye. There's going to be signs and indications and warnings of the potential collapse of that structure. And that's what we've got to keep an eye out on. Now, when a building collapses, a typical rule of thumb is for apparatus placement is to be 1.5 times away from the building as it is tall. So if it's a 20-foot tall structure, then we have to be 1.5 times away from it, so 30 feet away. That's a very good rule of thumb for any structure. It'll protect you from the structure physically falling on the apparatus. The thing that it won't protect you from is as a wall collapses and debris comes shooting out from the physical collapse, but it'll keep you from getting just destroyed as a wall falls on you. Define the following terms as they relate to building construction. A veneer wall is the very top right. A veneer wall is nothing but a wood structure with either a rock or stone or brick outside. It's the siding of the structure. That rock, stone, and brick has nothing to do with physically holding the structure upright. It's just for looks. Why is that important to us? Well, the first thing is that veneer is inherently stable on the structure staying straight. Once a wall starts to bow or buckle, that veneer is no longer going to be sitting on top of itself, and it's going to be leaning to one side. And what's holding that veneer up is literally nothing more than a couple of sheets of paper and literally some staples or nails. The other thing to be concerned of is when you're having to do a significant overhaul, you might be in your best interest to physically remove the veneer on the outside of the structure so that you can get to the hidden fire. Now, a party wall is going to be down here on the bottom left, okay? And that's a picture of 2 townhouses. And what you have is you have structures that are right next to each other, or buildings that are right next to each other, but there's no way to go from, let's say, townhouse A to townhouse B through that wall. It's a party wall. And then lastly, a firewall on the bottom left or bottom right is a wall that has built-in fire resistance to it, and it helps cordon off the rest of the structure and protect it in the event that there's a fire. Firewalls are fantastic. They're very common. And one of the easiest ways to identify a firewall is if you look at our picture on the bottom right, you can see how the wall itself physically extends above the roof line. That's a firewall. A partition wall is the bottom right, where you have like this office set off to the side, and you just these glass panels put up. The big thing you need to know about a partition wall, they're non-load bearing, and they also are very susceptible to collapse. So partition walls are something to be very cognizant of when you're on scene. Now, a cantilever or unsupported wall is down here on the bottom left, and they're typically seen in the form of barrier walls or basements. So you have this big concrete slab that's poured horizontally, and then from there, the wall is physically built up. And you can see that the cantilever wall literally uses the gravel and the dirt that it's holding back as a self-supporting technique. And that weight of that gravel and dirt sits on the footer, and it physically, as it's pushing out on the actual vertical wall, is a self-supporting wall. Now, a load-bearing wall is typically what you see at any structure where we have a fire, and that's always going to be associated with an outside wall. But don't ever forget that interior walls can definitely be load-bearing, and that certain walls in a house, maybe a wall that splits 2 bedrooms or a wall that splits a living room and a kitchen, may be an actual partition wall. There's no way to really know with some of these walls until you physically remove the sheetrock or whatever materials covering the wall. If you have any questions on these walls, ask us in class or make sure you ask someone at your home department. Identify causes of potential structure collapse. Deterioration, this is one that we've talked about for a while. This is just the physical fire consuming the building material. Now, forces associated with the violence of fire. As the building is starting to heat up, you have a large pressure increase inside the structure. You get a high pressure. So the walls are trying to bow out, the roof's trying to push up, the floor's trying to push down. That causes a large amount of stress on all the materials and the fasteners that are being held together. That is an example of a force applied. Now, another consideration with forces applied is as beams are removed or burned through, or as columns are burned or removed through, the physical opposite side of the structure, what's going to happen is the building tries to balance itself out. And lastly, structural modifications found during pre-fire planning. Structural modifications are typically going to be done by the business or property owner or homeowner, and it's when they go in there and unknowingly start removing load-bearing walls and they think they're partition walls. Now, the structure itself may not just collapse, but you introduce a fire in there and the structure will quickly come down on top of itself. Describe 3 hazards associated with lightweight truss construction. If unprotected, lightweight trusses can fail after 5 to 10 minutes of exposure. Now take that into consideration for a second. How fast is your department's response time? And then how long does it take you to actually get en route and get on scene? And then once you're on scene, how long does it take to prepare to make an interior attack? So you need to be really honest with yourself about this answer to that problem. I'll give you a great example. Granbury prides itself in that we have a very solid response for our area. And on average, it takes us 4 minutes to physically have a truck en route. And once the truck's en route, it takes us 6 minutes on average to get on scene. So 10 minutes has passed. Now let's go back to this. If unprotected, can fail after 5 to 10 minutes of exposure to fire. So we're not even set up for the interior attack, and the wood's not just burning, it's potentially failed. Okay? Lightweight truss construction is just absolutely terrible. Now, lightweight trusses can fail from exposure to heat alone. Why? Well, lightweight trusses are typically the wooden I-beams, and that's just a piece of particle board, and the board itself never has to be physically exposed to fire. That particle board's made up of finely divided wood particles, so it's got a high surface to mass ratio. And then on top of that, it's just held together with wood, held together with glues. So the glue itself becomes compromised just from heat, but at least the material that it's made up of off-gases really quick. Now, metal gusset plates can fail quickly, and they're due to just the fact that they're cheap, very, very cheap metals, but there's no full penetration when you physically put the plate through the wood, unlike a traditional nail where you would hammer it into a board and it would securely go through the board that you're attaching it to. On gusset plates, a gusset plate penetration into the wood is at a maximum of 1/2 inch. And then lastly, most lack fire retardant treatments. Adding fire retardant treatments to the inside of a residential structure is not expensive, but it is a cost, and their homeowners and home builders are always looking for places where to physically reduce cost, and this is one of the first places they go. Describe the effects of fire and fire suppression activities on the following building materials. So we're going to talk about wood first. As wood burns, it burns from the outside in. Okay, so we're going to just start with a real simple 2x4, and a 2x4, as it starts to heat up, it's going to start to off gas. That material is going to start absorbing heat. Now the outside of the material is what's going to absorb the heat first, and that's going to off gas first. As that material has off-gassed enough, it's going to char and it's literally going to vaporize away. And what that's going to start doing is allowing the next layer and the next layer and the next layer to start absorbing heat and start producing off-gases. Now, when you spray water on a burning structure like a 2x4, that water's physically going to cool that surface, and it's going to also help extinguish any off-gassing that's coming off, but the wood itself may physically have been heated up enough where there's enough heat stored inside the actual 2x4 where it's still going to produce off-gassing. So as you're in a structure fire and you're cooling a wood frame structure, you may have to run the physical water stream across that wood multiple times. Now, masonry, brick, block, stone. It's a fantastic material to build with. The problem with it is that once it takes a ton of heat to absorb into brick, rock, and stone. But once it starts absorbing heat, it's going to hold the heat. And on top of holding the heat, it becomes fragile. It breaks very easy. You could barely hit it with a tool and shatter the actual brick, block, or stone. Why is that a problem for us? Well, what are we doing in a structure? We're creating vent points. We're potentially having to extricate victims. We're having to remove parts of the structure for ventilation and evacuation. And that brick, block, and stone, once it's heated, it becomes fragile. And once it's fragile, that's not just one part. That's the whole wall, the whole surface that's now compromised. And combine that with load bearing, and it becomes fracturing very easy. Now, cast iron you're not going to see too often. That's more of an old legacy building material. Cast iron's very strong. It's got a very high melting point. The kicker with it is that cast iron shatters when it's cooled rapidly. So if you had cast iron that was glowing hot and you sprayed water on it, there's a really good chance it's going to crack and break. Now, steel, fantastic building material. We see it a lot in metal buildings and barns and shops, and it's a great material to build with. The problem with steel is that it does have a very high melting point, but steel, when it's rapidly cooled, it has a tendency to condense and pull down on itself very hard and twist. Well, that steel beam's intended to carry loads in a very uniform shape. And the second that steel starts to twist is the second that steel loses all of its strength. When you're inside fighting a fire and you encounter steel beams, it's imperative to continually spray water up on the beams to keep them cool. That'll allow you to continue long interior attacks. Whereas if you completely negate the steel beam and you forget to continually cool it, steel, though has a high melting point, does become very pliable at just a couple of 100 degrees, and then you add the combined weight of the structure, and what will happen is that building will start to sag and pull itself apart. Reinforced concrete, probably the absolute best building material out there. The only real complaint against reinforced concrete with structure is that as that concrete gets hot, there's a whole bunch of little water droplets trapped inside. Well, that water's going to heat, and it's going to turn to steam, and what's going to happen is that concrete wall's going to blow out pockets on the wall, and that's called spalling. Spalling is a sign that the concrete wall is starting to collapse on itself. Gypsum wallboard. Gypsum wallboard is the one thing that actually allows firefighters to make a legitimate attempt at trying to save someone's house. That's just a sheetrock. Sheetrock has got fantastic fire resistive properties. It doesn't burn. It has a great thermal barrier. The problem is a sheetrock is highly susceptible to water being applied. So as you're doing an interior attack, if you start squirting water in a heavily involved room, and you start noticing that you're punching holes in the wall and the ceiling with sheetrock or with your water stream, guess where you need to go searching for hidden fires next? In those walls and in that attic space. Glass is a rarely seen building material that we see in this area. Most of the time, the glass is responsible for the vent point in a structure because it just gets too hot and the glass itself just breaks and shatters. If you ever encounter a glass window on a structure fire that hasn't broken but it's very hot, when you spray water on it, it will shatter. Plaster and lathe, again, is a very old building material. When you do encounter plaster and lathe, it's got very good fire resistive properties to it, but the same thing, it's very susceptible to the water streams that firefighters are going to apply. Once the plaster starts to get wet, particularly behind the face, you've created a purchase point, a hole, and water starts to get on the backside, that plaster will crumble. Hello and welcome to the final class of Granbury Volunteer Fire Department's online fire academy, and we have a doozy for you tonight. We're going to be covering the art of reading smoke and building construction. Building construction is the last segment of SFFMA, and the art of reading smoke has been added to this entire presentation. Guys, our entire program and all the skills training you have done lead up to this one class. This one class is the icing on the cake and what's going to provide you with the last little bit of knowledge to start you off as a firefighter on your home departments. This is an awareness and perception class, and a lot of this is going to be subjective material that you might or might not see on scenes. But the purpose of this class is to teach you basic building construction and how to read the smoke from the fire that's burning in the structure. There's going to be a ton of notes to take. There's even going to be more questions to answer. And without further ado, let's start this class. The art of reading smoke is really coming from why do we care what the smoke is doing? And the reason we care about that is that we're going to be able to determine what is going on scene before firefighters make entry. The smoke, the characteristics of the smoke, and the story the smoke is telling us, everything that we need to know about the fire inside the structure that we're about to make entry on. Why learn building construction? Well, knowing building construction, we're going to know how the fire travels through the structure. We're also going to be able to determine other critical factors on the structure as we're watching the smoke progress, as we're watching the fire progress, and ultimately our hazard mitigation that should be expected with various types of structures. Why read smoke? To help find the location of the fire. Let's just look at the picture real quick. I'm going to ask you a simple question. There's no reason to even pause the slideshow. Where's the fire located? Is it on the first floor or the second floor? That's pretty obvious. It's on the second floor. Now, how do I know that the fire is not also on the first floor? Look at the front door. Do you see any smoke coming out the front door? No. That's how I know unequivocally that the location of this fire is on the second floor. If there was any fire on the first floor, there would be a small trace amount of smoke coming from the very top of that door. Even though the vent points are on the top of the structure on the second floor, there would still be some smoke trapped downstairs, and that smoke would be venting out the front door. Why learn building construction? Know the weak points of buildings. Be able to look at a structure and physically understand where it's going to potentially fail at or where it's going to fail at as the fire progresses or gets worse. Here's another thing to consider. It's also going to significantly help with the overhaul of the fire. How do we discover all those hidden spots and burning areas? By knowing our building construction. Why read smoke? To help predict collapse potential. As a command or as an interior firefighter or as an officer on a fire crew, we are always working around the potential collapse of a structure. And understanding where the fire's at, understanding the intensity of the fire, and the ability to understand the building construction as a whole will all help you predict the collapse potential of the structure. Why learn building construction? Prevent a building from collapsing on our fire crews. Knowing the structure and knowing how the fire compromised the structure is ultimately going to lead to safer fire crews on scene and potentially eliminating an absolute catastrophic event from happening on scene. Why read smoke? To help prioritize strategy and tactics across all levels of the fire department membership on scene. If the basic firefighter understands building construction and reading smoke, and if the basic officer and the command officer and ultimately the fire chief, if everyone across the board understands what the smoke is doing, what the smoke is telling you, and understands building construction, it's going to help those members quickly and appropriately build a strategy and tactics for the attack and extinguishment of that fire. Why read smoke? To protect firefighters from a hostile fire event. Again, you've heard me reference several times flashover. You went over it in detail in the fire behavior class. The flashover event is the only fire event that we truly care about outside of backdraft. And since backdrafts are so exceedingly rare, what we will potentially see every single time on a container fire, no matter whether it backdrafts or not, is a flashover. Flashover awareness is what we're after. And again, what is a flashover? Flashover is when the smoke in the container begins to burn. The flashover events are incredibly violent and they're incredibly hazardous to the interior crews. The advanced concept. Concept number 1. Smoke is fuel. It's the new 4-letter F word. In the smoke, what's truly in the smoke are gases, particulates, and aerosols. Now, I'm going to go into detail on each and every one of these, and I'm going to start with the fire gases. The fire gases are the product of a heat buildup in a room, and the solid materials in the room start to off-gas. Those are the gases. The particulates are the fine particles floating in the room as a product of the combustion. And think of it as just a whole bunch of charcoal floating in the room. And they're finely divided particles. And what did I tell you about small particles? And lastly, aerosols. Aerosols are the product of the combustion process. They're the byproduct of the actual fire. These are the toxic buildup in the room. It's all three. They're all flammable, and they're all truly surrounding you and ready to burn you. The advanced concepts. Concept number 2. Fuels have changed. Mass and makeup. And what I want to go into here is on just the difference between old and new construction, and I want to just talk about a few main points. The first one is just the construction materials themselves. A new house today is virtually built out of everything that they can get that is lightweight material. The reason for that is because we want the house as cheaply built as possible. Instead of plywood for roof decking, there's particle board. And instead of full truss construction with true dimensional lumber, we use new engineered beams that are pressed together, glued together, and then they have gusset plates installed. There's nothing physically connecting the board to the other board outside of what the gusset plates connect. The lightweight construction is through the entirety of the structure, from the floor to the wall to the ceiling to the roof. Lightweight construction is fantastic for construction bills, but the reason we call it lightweight construction is because it is cheaply made. At the end of the day, it is cheaper to build out a particle board than plywood. Bits and pieces of different trees glued together is cheaper than a true dimensional piece of lumber. The second thing I want to talk about is what physically makes up the contents of the house today versus what was there 50 years ago. Today, structures are filled with hydrocarbons, oil-based products, and it's in everything. Again, we know why that's bad, because they off-gas at a low temperature, they burn at a low temperature, but at least when they're burning, they burn for a long time, and they produce a massive amount of heat. Whereas 50 years ago, the contents of structures were primarily based off of wood and cotton, a handful, and this would have been the dangerous part of a structure, the lacquers and the thinners, but there was very few glues used at that time. Almost everything was put together with nails. The chairs were stuffed with cotton or feathers. They weren't filled with foam. Things like pleather didn't exist. It was either cloth or leather. There was no difference. The old materials did not produce off-gas easily, and when they did start to get hot, they didn't produce a ton of off-gases. Moving into new construction on the insulation and airtight side. We want, in a new house being built, we want it to be as airtight as physically possible, because the less air that leaks, it means the less it takes to cool or heat that physical structure, in combination with how good the insulation rating is. So if your house is well insulated and it's airtight, it's going to be very efficient. But on older construction, those houses were not airtight. They had more leaks on them than the Iraqi Navy. It was impossible in old construction to physically make your structure airtight. Why does that matter? Because the smoke that's being generated inside the structure and the heat that's being generated inside the structure physically get held in tighter. Now, there's a couple of factors that we're going to talk about in this particular slide. Old and new construction. The main threat to firefighters face today. We have two houses here, one on the left and one on the right. The one on the left is obviously looks a little bit older, and it is. It's older construction. That's called balloon frame construction. And balloon frame construction is a building technique when they would physically build the walls on the ground and then raise them as one giant panel. How do you identify balloon frame construction? Well, the first one is just look at all the windows in the house. All the windows are in a perfect symmetrical line. There's no windows offset from each other. And they do that because of building techniques and the strength of the walls. Here's the problem with balloon frame construction. It creates gigantic void spaces in the wall. And you could have a very small fire on the porch that maybe burned through a small hole in the wall that was following, let's say, a telephone line, and then once it was in the wall, it lit the insulation in the wall. I guarantee you that fire is instantly going to run to the attic. Let's go to the right picture, newer style construction. You can see that the actual windows of the structure aren't necessarily lined up with each other, and on top of that, they're different sizes. This is indicating that it is not balloon frame construction. Another thing to take into consideration is whether it's pier and beam or whether it's slab foundation. Pier and beam construction is an example of over there on the left picture. The house is physically elevated off of the ground. The reason it's elevated off the ground may be because it's in a floodplain. Maybe it's built on a slight incline. We don't know and we don't care. The house itself is physically elevated and it creates a void space under the physical structure, whereas the house on the right is built on a foundation straight on the slab. There's no void spaces under this structure. Now, one side benefit of new construction versus old construction, I've already addressed the void spaces in the wall, but at least new construction is a lot more segmented and compartmentalized. Your ability to have a fire in one room is going to be able to maintain that fire in one room for a longer amount of time. The problem is again, the materials that physically fill that room, you're going to have a much bigger, hotter, and vigorant fire versus what you would have on an old construction house versus new construction in the physical contents of the room. New construction and energy requirements. One thing to factor into new building construction is the cost of utility bills and everyone trying to reduce the cost of their utility bills. We'll just start at the very top. You have new insulated roofs or potentially solar panels that make up the roof. And the roofs themselves, they work great for reducing energy costs, but what does it do with the heat inside the structure? Well, it's going to trap it inside. Concrete block walls with at least a minimum of R8 insulation, and then more importantly, sealed to prevent airflow. How does that hurt us with the fire? What does reduced airflow to a well-established fire do? We're going to have more backdraft potential in the near future with the new building construction. Solar panel ready roofs and electrical. Not only with all the solar panels on the roof, but think about the extra electrical load physically going into the structure. What type of hazards does that create for the firefighters? But also on top of that, how many new electrical ignition sources are potentially there for the firefighters to encounter? And lastly, how do you secure the power to a solar-powered roof? Native or drought-tolerant plants. Well, frankly, that one doesn't do anything to us. So we're going to move right to the next one. Solar reflective roofing and exterior paint Energy Star certified. How efficient is that new paint at reducing an electrical bill? Probably pretty efficient. How much dangerous crap went into the production of that ultra efficient paint? Built-in moisture, radon, and pest controls. So we're permanently adding chemicals and pesticides and rodent control to the structure. Well, same thing. Those are gases and liquids and solids that we're adding to a structure, and what happens to those chemicals as they start to heat up? What about the new doors and windows that are energy certified? All they're doing is preventing airflow. Again, it's another backdraft potential scenario setting up. And then finally, your HVAC systems. How much airflow are those HVAC systems required to move into the structure now that the structure is fully sealed? It's going to be one of the primary vent sources for intake of a structure fire. Advanced concepts. Concept number 3. The fuel has triggers. Again, guys, we cover this stuff because there's some of this is requirements per the state. It's kind of important to understand this just in a fire behavior and art of reading smoke point of view. I don't really care if you memorize these definitions. It's just important to know some of this material for in the event that you ever take the state test. So first one, flash point. Flash point is the lowest temperature at which vapors of the material will ignite when given an ignition source. So in other words, we have something that's off-gassing, and those vapors will ignite if I hold a heat source to them. Fire point is the lowest temperature at which the vapor of the fuel will continue to burn for at least 5 seconds after the ignition by an open flame. Fire point is the sustained fire. So if we have a fire and the gases catch and they immediately go back out, that's not fire point. You got to have it burning for at least 5 seconds. Ignition temperature. The auto-ignition temperature or kindling point of a substance is the lowest temperature at which it spontaneously ignites in the normal atmosphere without an external source of ignition such as a flame or spark. Ignition temperature is one of our indicators of flashover. When you have thick, dense, fast, black-moving smoke out of a window, and the smoke physically catches on fire outside of the structure, we have not introduced a heat point to it. We've not thrown a cigarette or a match or a lighter or a hand grenade at it, but it still spontaneously combusts. That's the ignition temperature. Ignition temperature is flashover. Those triggers, also and combined with the temperature and the fuel to air mixture ratio, create a flammable range. And the flammable range is what we're ultimately after here. Now, if you look down here at the bottom left of the slideshow, you see a structure that's showing heavy smoke, and I don't see any fire out of it. But if you look at this structure, you've got smoke coming out of the first and second floors, out of all the windows, and out of all the openings. I know that's a very well advanced fire, and I know that's a very hot fire by simply just looking at the volume of smoke coming out of that structure. Now, if you look at the top right picture, you can see when this smoke is physically ignited. What has happened is the smoke is now hot enough. We know there's plenty of fuel in this smoke, and there's enough oxygen finally involved with the smoke to actually create the fire. Now, one thing to consider with this is it possible that the fire is not developed inside yet? And the correct answer is yes. The fire could very well only be outside the structure where it's venting from the structure. And in this particular case, you can tell that by just the physical, literal large flames that is coming out of the smoke, out of the structure. Right now, the atmosphere is literally burning outside of the structure. Not the structure itself, it's just the smoke. Flammable range and the three fires. What we're going to look at is a fire that's too rich, a fire that's too lean, and a fire that's burning perfectly. And we're going to start with the bottom left picture, a fire that's just too lean. You can tell that there's very little smoke. There is color to it, but there's just not enough smoke there. There's not enough fuel there. And since there's not enough fuel, you don't have a raging fire yet. Now let's go to a fire that's actually the exact opposite. Let's go to too rich, where there's a ton of fuel, but the fire itself has consumed all the oxygen inside the structure. And what we have is a fire that's not burning at its full potential, even though all the factors are there. And that's a fire that's too rich. Now, the fire itself will ultimately balance itself. Physics will take over and chemistry will prevail. And that mixture will occur naturally. And when it does occur, you go to the bottom right picture, you have a fire that is burning completely out of the control. Now, one thing I do want to point out is the picture on the bottom right, that's obviously a garage fire, and there's no door down. So even though there's a large fire in the garage, there's nothing there to physically restrict the actual airflow into the structure. So that fire was able to go straight from growth rapidly and straight into flashover because of the walls and ceiling of the garage. But there was nothing there to prevent the oxygen intake of that fire. Whereas if we go to the picture at the top where it's too rich, there's only a handful of windows open on this structure, and those windows aren't big enough to allow enough smoke to eject from the structure and enough clean, fresh air to come in to actually sustain the fire, to ignite the smoke and grow the fire any further. But there is a massive heat buildup nonetheless inside the structure, and it's being propagated by the massive fuel load inside the structure. Sooner or later, this fire will get a vent point big enough, and it will allow the atmosphere to catch on fire and burn. What we are taught versus reality. I know you guys have seen these slides a lot, but I want to go over this again in our academy. What most people experience in the form of fire behavior and what they're taught's the graph on the left, where you have an ignition source, the fire grows, it's fully developed, and then we go into decay. And right after it's fully developed, on the left side of the graph at the peak is where flashover occurs. But in actuality, if the fire doesn't vent itself, then the graph on the right is the graph that we have to be cognizant of. So we start again at the ignition point, we have a self-sustaining fire, and the fire is going to grow until the fire is underventilated. The structure didn't fail. We didn't have a large enough heat buildup in the structure to cause the structure to fail and create its own vent source. At that point, the oxygen in the room will be consumed by the fire and it will start to die down. Once the fire department's on scene and once it makes entry at the front door, a vent source is created. Once that vent source is created, and that is the only vent source, from there you now have oxygen being delivered back into the structure, and you will have a rapid temperature buildup just because of the definitions we went through a few slides ago. The precursors are there. Everything's built into just needing oxygen. If the firefighters are not quick on their entry, the fire will, one of two events will happen. It will either potentially backdraft or it will potentially flash over. It doesn't matter which one because our crew's dead anyways. They have to have action on the fire and on the atmosphere of the structure before those two events. If they get there and they get there in time, they'll cool everything down and no event can happen. But for whatever reason, if they're delayed, once the fire flashes or backdrafts, you're immediately fully developed. Then the fire will consume the materials inside the structure. Building construction and the effects on fire behavior. Guys, what I want to talk about is new building construction here. And you always hear me talking about these gusset plates, but this is a great picture of a gusset plate that I found in a structure here in our area. This was a smoke investigation in an attic, and if you've ever met me, I'm like a ballerina. I can dance from rafter to rafter like a cat. That's not really the case. What ended up happening is I stepped on this rafter and damn near fell through the entire roof of this, or correction, the ceiling of the structure. So of course, I'm going to see what happened because I didn't just blunder and fall. The entire actual roof gave away, the truss gave away on me. So I looked at it and I saw this gusset plate had completely been torn from the wood. This is how gusset plates are attached. They're just placed on the rafters and they're nailed in. And if you look, there's no penetration on that wood. That's not a solid penetration of the wood. Not to mention, what type of material is that made of? It's a cheap metal. It might work in perfect conditions. It's not going to work on a high heat load. Let's look at the picture on the bottom left. These are called wooden I-beams. I'm starting to see these all over the place here. Now, wooden I-beams are fantastic because they're a cheap building material. They don't cost much money to buy. They're cheaper to make, and they're very strong. Here's the problem. Wooden I-beams is nothing but particle board with two top rails, or a bottom and top rail, that literally makes an I-beam shape. They're easily compromised under two things that firefighters provide readily: heat and water. Wooden I-beam's nothing more than particle board. The particle board, once it gets hit with water, is going to start to swell. And on top of that, if the particle board's exposed to heat, the glue gives away really quick because it off-gases quickly. The combination of the two, a lot of firefighters have been killed by wooden I-beam construction, and some states have even gone as far, like in Florida, it is legally required to post on the outside peak, on the street side view of that peak, that you have a wooden I-beam construction. Other prerequisites to reading smoke. You must be able to determine two things. The first one we're going to look at is the stage of fire growth. Obviously, we want to make entry into the structure before flashover. We do not want to make entry into the structure at late stage growth right before flashover. We have to be able to determine from the smoke, is it safe to make entry into the structure? That's the whole purpose of doing this. So if we look at early, middle, or late stage growth, we're making a determination off of that stage. Here's a really big one that's going to help you determine, is it early, middle, or late stage growth? And you'll have to see a couple of structure fires to really feel this out, but once you really make this connection, you're going to really appreciate this little bit of information. Is the box absorbing heat? How do we know if the materials inside the structure are physically absorbing heat? Well, is the smoke coming out of the house laminar or is it turbulent? Laminar means smooth. Turbulent means very rough. So if you see a laminar smoke flow, a very smooth smoke flow, you have an early stage fire and the heat is still physically being absorbed into the products inside that house. If you have a very turbulent smoke flow, that is a very late stage growth fire, and you need to be prepared and your eyes open for a flashover event. The next slide we're going to look at is really going to explain this very well. Look at the actual smoke of these fires coming from these structures. I don't care about the physical structure. I want you to look at the smoke. And let's start at the bottom right. Okay, we've got a nice two-story house, obviously wood frame construction. Definitely fire coming from the second floor. Looks like primarily from the attic space. Let's look at the smoke here, though. That's a nice, smooth smoke. It's you can tell that it's coming out of the structure, but it's not being pushed. It's not heat driven. The reason that's important to us is because the heat is still being absorbed by all the materials inside. This is a early growth fire. Early growth fire. It still may be a large fire, but we're early in the growth of this fire, and this is just by the determination of a nice laminar flow. Let's go to the top left. That's obvious. That's a serious fire. Again, ignore the structure. Look at the smoke. That smoke is hot. There's a ton of it. It's very dense. So where's the heat going now? If all the materials inside have absorbed the heat, where's the heat going? Well, the heat's going to the atmosphere, and now it's trying to push out. It's trying to push out violently. It wants out of the structure, and it's going to push hard out of the structure. If you see laminar flow, you have an early growth fire that's not going to be very hot. If you see turbulent smoke, you know that is a late growth fire, and it's going to be very hot. Definitely circle this, underline it, do whatever you have to do to remember this. Because as a firefighter, you showing up, we see this picture on the bottom right. Man, this is where you should be excited. This is going to be a great fire for an interior attack. You are going to be able to make a fantastic entry. You're going to march straight upstairs. You're going to pull some ceiling. You're going to squirt some water in the attic space. You're going to get your thermal imager out, and you're going to find that small fire real quick. You go to that picture on the top left, you get dispatched to that, and you're just going to be like, we're going to be here all day, because it's already a late stage fire. You can look at these two pictures and tell the difference on what you would make entry on and what you wouldn't. Here we're going to go into hostile fire events in more detail. Flashover, backdraft, smoke explosion, and then rapid fire spread. Flashover. Here's the warning signs that flashover is imminent. Very turbulent, dense smoke. Rollovers visible while making the interior attack. Rollover is you're going to start to see different gas layers at the ceiling start to ignite, and the fire is going to roll down the ceiling trying to get and consume all those fire gases. Here's the problem. What's that fire rolling through those different smoke gases? What is it releasing into the other smoke and atmosphere around it? More heat. It's prepping the atmosphere for the full event. Auto ignition outside. If you're starting to see the smoke automatically ignite the second that it's outside of the structure and it is venting at that point, that is a dead giveaway that you have flashover conditions inside the structure. And if you have a crew doing an interior attack right now, they need to start squirting water either on the fire this second, or they need to start cooling the atmosphere that's around them, and they need to plan on getting out if they're not at the seat of the fire, extinguishing the fire right this second. Smoke cloud ignition is likely after flashover. We will see the smoke inside and outside the structure begin to burn in its entirety. Just some building construction on flashover potential. Another picture of wooden I-beams, but hey, at least this time they're weakened by having contractors drill through them. Not to mention, look at the spray insulation on the left picture. What's the spray foam going to do as it's exposed to heat? Well, it's going to burn away pretty quick. And what's that spray foam in this particular picture doing? It looks like that it's trying to isolate from wherever that pipe's going into the other room. So now you have another potential vent source and a direction for the fire to physically travel to. On the bottom right picture, we have an attic that's been spray foamed. Yes, it's fantastic for energy conservation, and there'll be a very cheap electric bill associated with this structure, but let's think about the heat buildup in this room, and let's think about the actual off-gassing potential in this room. Going into an attic like this is the effect of walking into a crematorium. Backdraft. Backdraft is triggered by oxygen being introduced to pressurized smoke that is above its ignition temperature. Again, just to recap on backdraft, you have a hot fire that has consumed the oxygen from inside the container, and you have a massive heat buildup and a massive smoke buildup inside that container, and now all we need is the oxygen. And if that smoke inside that structure is above the temperature for ignition, you have a strong likelihood or potential of backdraft. Now, recognition signs. We're looking for yellowish smoke, listening for a whistling sound. Is the smoke being forced hard out of the structure and being forced hard out of the structure in unusual places? Bowing windows or browning windows, or just completely sooted out windows. Windows that show that there's been heat and smoke in the room, but there's no visible flame. And then also sealed containers. Any building that you know is a particularly tightly sealed building and is going to it's an obvious lack of oxygen inside the structure. Backdraft potential. Old construction, it was very rare because the structures just could not be sealed up. New construction, we should start to experience this a lot more often. Texas is a hot state. Texas has had very cheap electricity for decades. Just recently, electrical prices have gone through the roof because Texas has realized they can sell all their electricity to the states around them. And for a fantastic fun note, if you didn't know, there's 3 electrical grids in the United States. There's East, there's West, and then there's Texas. That's how big the Texas electrical grid is. It's its own subsection. Back on point. The reason electricity got expensive is the cause of why everyone's trying to make their houses ultra efficient. People do not want to spend a ton of money on their electric bill, and they started to go to great extremes, not only in remodeling a house, but particularly during the construction phase where it's the cheapest, to go in and make your structure as usable as physically possible, but cheap. And they started to use ultra-efficient insulations. They started to use ultra-efficient windows, ultra-efficient roofing materials. They started to wrap the house. They taped and bedded every gap, and then they wrapped the foundation in plastic. They sealed the house truly from the environment outside. This way, your air conditioner, when it puts out cold air, or in the wintertime, hot air to heat it in the winter, that air does not escape that structure. This is the problem. These houses are well built enough, and there is enough petroleum byproducts inside, hydrocarbons inside the structure, that the fire can potentially snuff itself out, but release enough heat and enough smoke into the atmosphere that we could potentially start seeing a lot more backdrafts. Keep your heads on a swivel. Smoke explosion. A smoke explosion is a spark or a flame applied to smoke below its ignition temperature. Only some of the fire gases ignite. What's going to happen here is, again, remember, you're going to have multiple materials inside the structure off-gassing. And in a smoke explosion, only some of the fire gases inside the structure caught on fire in a mini backdraft, and you're going to have a massive heat buildup because of some of those smoke layers caught on fire. And as you have a huge heat buildup, those particles are going to spread apart, and what you're going to get is this giant cloud of smoke that's going to come blowing out of the front door. It's going to scare the crap out of you, but luckily it wasn't a backdraft. That is a smoke explosion. Luckily, after the smoke explosion, the fire will be back to a free burning stage, and you should be at flashover. Things to look for: trapped gases in upper areas. Does the structure you're in have a vaulted ceiling? Does it have an area where the fire gases can be trapped? A growing fire, not fully developed, a growing fire. The smoke is increasing in density. The heat buildup is enough in the room to start getting more materials to off-gas. And ultimately, the air intake is overtaking the smoke exiting. The fuel-to-air mixture ratio is starting to balance. Our last hostile fire event, rapid fire spread, is usually container influenced. Again, the structure is going to dictate primarily whether you have a flashover, because you have to have walls and a roof in place. If the fire's already vented, these events can't happen. The container itself has to be intact. Smoke is the fuel that's spreading the fire. The smoke is the massive heat source preheating everything for the fire spread. Look for fast-moving smoke in high-pressurized zones. That's the hottest part of the fire. That's going to be the seat of the fire. And as an interior firefighter, that's where you need to work to. And ultimately, rapid fire spread may occur from the result of another fire event. You may have just had flashover where the entire atmosphere is burning. You may have just had a backdraft and the structure is potentially leveled or has caused flashover now. These hostile events will also increase fire spread in itself. Looking at building construction with rapid and hostile fire events, let's look at the modern open floor plan. Once you have a fire that's established in this structure and you start to have a smoke and heat release from that fire, where's the smoke going to go? Well, technically with this floor plan, it's going to go everywhere. Here's the consequences of that and benefits. The first one is it's going to take a longer amount of time for that fire and smoke to effectively fill the container and have the full effects of preheating the room. Here's a consequence. The room's already jam-packed full of a giant void space of usable oxygen for the fire consume. So it can, once it's in growth phase and as long as it has fuel, that fire's going to burn hard. Now, let's look at a little further development into the actual fire. Once the fire's established and you have a large smoke column building inside the structure, and once the heat begins to truly build in the structure, how hard is it going to be to actually make entry into this structure and potentially find the seat of the fire? On top of that, if you're inside a structure like this and it feels hot to you, what does that really tell you about the size and the true conditions inside the structure? That's telling you that the fire is getting very close to flashover. And then ultimately, the final event, when flashover occurs, it'll be a truly biblical event. You're going to have a truly gigantic fuel source in the smoke that's just waiting for ignition. Application rules. Observations are typically made from outside the structure. Inside observations hide the real picture. So let's look at our structure that's showing smoke down below. We can tell that this is a 2-story wood frame house, and we can tell from where the firefighters are standing at the front door, and it's obvious that fire crews are making entry in the front door and the front door is open, that there's no smoke coming out of the front door. So I know from this picture that the fire is definitely on the second floor. Also, let's look at the smoke itself. There's a relatively large volume of smoke associated with this, so I know that the area itself is starting to be exposed to a lot of heat. But let's look at the physical velocity of the smoke. That smoke doesn't look turbulent. It still actually looks like it's kind of lofting out of the house. But let's look at the full structure. Let's look at that left eave. I see a very long laminar smoke line running down that eave. So again, there's a large volume of smoke. It's just not that hot yet, and it's on the second floor. If I'm a firefighter and I never looked outside of the structure and just went straight in for the interior attack, what's the picture that I see? Well, there'll probably be very light smoke downstairs, but once I'm upstairs, I'm going to be completely inundated with smoke, and my visibility is going to be almost absolutely zero. I'm going to have a hard time locating the fire, just short of using a thermal imager or any other electronic methods. Sight and sound probably won't help me too much in the location of this fire. By looking outside and looking at the smoke plume towards the middle of the picture, and it's behind the power lines, I start to see a vertical column of smoke. That's probably a vent source, and that's probably where the seat of my fire's at. And I can look at this picture and realize that that fire's in the middle of that structure. Visible fire is easy to read. Look past it for the real story. Compare vent openings. In this picture, you see a McDonald's, and you can easily see firefighters going in the front door or a side door on the left side of the picture, and you can see the fire venting out the roof right there in the middle of the restaurant. What you don't see until you really look at this picture is the smoke column. And I realize this isn't the best picture in the world, but that smoke column is literally the entire width of that room. It's the entire roof space that is the smoke column. So now that we realize that that's the actual smoke column, how big is this fire? Well, it's gigantic considering just the size of the structure. Should those firefighters be making an interior attack with a building showing that much fire loading? Consider the construction of the building. It's a McDonald's. How well built are those structures? They're not. They're kit buildings. They're put together as cheaply as possible and as quick as possible to start making money. Those buildings are insured to burn down and be rebuilt in 30 days. Let's look in the dining room windows. You can see lights inside the structure. You know the fire's not on the first level. It's obvious the fire's in the attic space. What's the only way into the attic space of this picture? Well, you have to make an interior attack and work off of ladders to be able to get up into the attic space. Here's another thing to consider. What's the actual construction of that roof? Is that a pitched roof or is that a flat roof on top? That's going to be a flat roof on top. And what's on top of flat roofs? Air conditioning units. And the air conditioning units are what killed that firefighter crew you see going in the front door of this McDonald's. You have got to pay attention to the whole story. Just because you see the fire does not mean that you grab the hose and just sprint into that structure. This is a massive fire. It's a well-involved fire, and this fire is obviously compromising the structure just due to the color. It's a heavy black smoke. And then lastly, knowing building construction, I know that there's air conditioning units on the roof of this structure, and the combination of the serious fire development, knowing the story from the smoke and understanding the building construction, we're not going anywhere near this thing. Using the art of reading smoke, we start a process to help predict the fire behavior and hostile fire events. Now, let's look at this picture really quick. You have guys that are making entry right now at that front door. And what did I say earlier about smoke igniting outside of the structure? Let's take a look further at this smoke that's actually coming out of this structure. Is that laminar smoke flow at that eave, or is that an awning over the house that's actually trapping smoke there on the front porch? And it's, if you look at the little deeper into that awning, you can see that that smoke is boiling out of that structure. These guys have no business making a straight interior attack right here without cooling the atmosphere first. Get the smoke cooled down, then make entry. There's nothing wrong with that. Those are solid firefighting tactics. Here's something else to consider. Why not move down to the window and have another crew down there just spraying from outside straight onto the fire that's coming through that window, and start cooling that room right now from outside, so that that crew making the interior attack at the front door doesn't have to worry about continued fire development from the seat of the fire. Step 1, evaluate the key attributes. When we're looking at smoke, we're taking into 4 factors for consideration. We're looking at the physical volume of smoke, we're looking at the velocity of the smoke, we're looking at how dense the smoke is, and ultimately the color. Volume. Volume of smoke is always relative to the size of the container. And here's a trick question that I want you to think about real quick. Would you be more concerned about a fire inside a structure that is very small but showing very heavy dark black smoke that's boiling out? Or would you be more concerned about a gigantic structure with a very thin smoke layer at the ceiling? I'm going to give you a second to think about that. The volume of smoke presenting with the structure should be taken into consideration with the size of the structure. If a very small structure is showing a ton of smoke, heavy dark black smoke, well, that's to be understood because it is a very small structure. The space inside that structure is going to fill rapidly and then vent out of that structure. But if you're at a huge big box store and you look up at the ceiling and you see a real thin layer of smoke that's up there at the ceiling, you should be seriously concerned about that fire in that structure. Because think of how much space and volumes inside the size of something like Home Depot, Lowe's, Walmart, Kroger, and H-E-B, and how much smoke it would actually take inside the structure before you would even get a visible layer of smoke at the structure. The smoke levels inside a structure and its size is a huge indicator to tell you how much fuel has off-gassed. Now, it'll also tell you the stage of the fire just by looking at the physical color, and we'll go into color in a second. Now, this is a building construction question. How will the fire travel in this building? Well, let's look at the building firsthand. This is a strip mall, so we know that this is a bunch of individual businesses that are walled off from each other. But here's my question to you. What does the attic space look like in this structure? And you already know the answer. You know that the attic space is a giant open space. It's a common attic space between all businesses. If the fire gets to the attic space, it's going to be able to run the entire length of the building. The design and engineering of these buildings in regards to firefighting is very, very, very difficult. Now, let's take a look at our picture here, and let's take a look at the smoke on this. We see interior crews working in front of LV nails. We see a front door open and a pretty good black layer of smoke coming out of that door. Let's look at the back of the structure. I see gray smoke rising from the roof, and I don't see any gray smoke coming over from any lab tests now or any other business to the left of the nail salon. So I know that fire's centralized to the nail salon. Here's my last question. Is the fire just in the business space of the nail salon, or is it in the common attic space? Take a look at this. Let me know what you think and write your answer down. Drop ceilings are very common in any structure with a flat roof, just like our previous slide with the nail salon and in the strip mall. A drop ceiling is that sheetrock tile ceiling that comes down from the fixed roof of the structure, and that's where they're running all the electrical, that's where they're possibly running the plumbing, that's where they're running the telephone lines, the internet lines, and all the HVAC lines for all the businesses in the strip mall. So a drop ceiling can shield the fire from the firefighters, and you can walk into a structure and not even realize the fire's above you. When working with the drop ceiling and you suspect there's fire above you, start knocking out the tiles and start getting ladders and get some eyes up there with the thermal imager to see where the fire's at. Now, another consideration with the drop ceiling is physically working from the roof of the structure. If you do a trench cut, what you've seen right here in this picture, what you also have to remove is the drop ceiling from the actual room and contents fire. That's the only way that you're going to be able to get all the heat, all the smoke, all the fire gases, and all the aerosols out of that structure to vertically ventilate. Velocity. How fast is the smoke leaving the compartment? Velocity can indicate volume and or heat, but it also helps us find the location of the actual fire. Now, this is one of the best smoke reading pictures that I've ever seen, and we're going to go into great detail on this picture on the left. What I want you to look at is just the whole picture. It's obvious that this fire's definitely on the third floor. We can see where the smoke's venting from all the windows and the eaves on the third floor and from the attic space. But I also want you to look at the far left of the slide. You see how there's nice, relatively smooth white smoke pushing out of the structure on the eave. And then as we continue to move across the structure to the right, we get to a dormer window, which is halfway in between the black window on the right and the smooth smoke on the left. That dormer window shows a completely different picture than the smoke on the left. We're starting to see that it's bubbly, we're starting to see that it's indicating volume, and we're starting to see that it's indicating pressure, and that pressure is derived by heat and volume. This is a ton of smoke leaving this structure, so it would make sense that with it being highly pressurized in the structure, the smoke's going to be forced out. And then we can also tell from the smoke color that it's also very hot. And then ultimately, as we work our way to the right and we look at the very last picture on the right, that's very, very dense smoke. There's a ton of actual smoke coming through that column. It's very dense smoke. And then lastly, the color. Velocity is a huge indicator of the stage the fire's in. This fire's definitely in late stage growth. This is almost a fully developed fire. How is the building affecting the smoke pressure? Let's take a glance at this building at face value. This is a single-story building, looks like it's stucco on the outside, and it looks like it's got a very tall roof. Let's look at the smoke. There's a massive amount of smoke coming out of this structure. Let's zoom in a little bit more. At the front door, you can see that there is a very definitive clear patch of air for the intake going into the structure. And above that, you can see smoke and fire at the top of that doorway. We know that we have free fire burning inside, and it is not being inhibited at all by the lack of oxygen. So with that fire continually growing and burning, it's going to be producing its maximum amount of heat and off-gassing related to that heat. I have a sneaky feeling from looking at this picture that we actually have a vaulted ceiling inside this house, and part of the reason that I'm saying that is just strictly by the massive amount of volume of smoke coming out of the structure. Those vaulted ceilings are going to be a bigger space for the smoke to sit in, but more importantly, with the vent point being down low, all the smoke and the fire gases trapped in the vaulted ceiling are physically getting heated more. And because of the vaulted ceiling, we're able to trap more of the smoke and off-gassing that's occurring. And it's just this redundant cycle. The more heat, the more off-gassings, the more it's going to be trapped inside that space. The bigger the space, the more the heat can hold, the more the physical smoke can expand. And that's how I'm looking at this structure with the massive amount of smoke coming out of it versus a vaulted ceiling. Density, the single most important factor when evaluating the smoke. The density of the smoke is going to tell you the quality of the burning, the continuity of the fuel, the likelihood of an event, and ultimately the degree of the event. The quality of burning. The more that an object is being preheated and off-gassing, and the more the complete combustion process is, the cleaner the smoke. And the absolute best example I can give of this is a natural gas stove and igniting the burner. The natural gas coming out of the stove burns almost 100%. There's no smoke physically coming off of that fire. Why? Because the fuel is being consumed 100%. Now, the density factor, or the quality of the burning, or the density factor in relationship to the quality of the burning, the more thick and the more dense that smoke appears to be means that you have something that's limiting the ability of that fire to consume the fuels in the smoke. That factor is going to be oxygen. Continuity of the fuel. Continuity is just how much of the fuel is physically available, and is it a continuous fuel source? In other words, is it in small little piles where the fire is going to have to burn and then leapfrog, or is it in one long chain where it's easily transferred? Density is also going to indicate the continuity of the fuel. If we have really thick smoke and then the smoke dies down and it's not as thick, and then we go right back to a really thick smoke and then it dies back down, we know we don't have a good fuel continuity. The density of the smoke is also going to be the indicator for a likelihood of an event. The more dense the smoke, the higher the chance. And then ultimately, the degree of the event. If we look at smoke as fuel, and if you take it, the density of the smoke is very thin or very thick, how much fuel is physically available in a very thin smoke? Not much. What about a very thick, dense smoke? Well, you now have a lot more fuel in place, and in the event when it happens, you're going to have more fuel to consume. Now lastly, when we get to smoke color, we're going to cover a couple of different slides here. Different colors of smoke mean different things. What does white smoke tell us? Now, there's a big difference between white smoke and steam. When steam's applied to a fire and a steam cloud's generated, the further that steam gets away from the fire and the more that steam cools, it's eventually just going to completely disappear. We're going to watch it fade away very quickly. A white smoke, once it's in the atmosphere, it's not going to dissipate. It's not going to fade away. Now, it may thin out, but the smoke itself as it moves up into the atmosphere is going to still be present. Now, what does the white smoke physically tell us about a structure? And if you look at the picture at the right, you can see a firefighter standing in a very, very dense white smoke cloud. We're going to come back in just a second, but what do you think the reason is that smoke is so white? The reason the smoke is so white is because it has traveled throughout the building and it is being filtered. Best example I can give you to think of is if you have the fire on the opposite end of the structure, but it is a very large fire, it's a very hot fire, and it's generating a ton of heat, you have a massive buildup of smoke throughout the structure. As the building becomes pressurized, the smoke is going to move across the structure, and it's going to be pushed into the floors and the walls and the ceilings. And in this case, the smoke's exiting from a wall. And walls are typically filled with what? Insulation. So if the smoke is being pushed through insulation, the insulation itself will act as a filter, and by the time the smoke is exiting the building, it can be pure white. Smoke is telling you that you have a deep-seated fire when it's white, and that the fire, the smoke that you're currently seeing, is traveling a long ways. The other thing it's telling you, you're in the exactly wrong spot. You need to move to the other end of the structure. Brown smoke. When you show up on scene and you start to see a lot of brown smoke, something very specific is starting to happen. And what I want us to look at here is at the garage opening at the bottom right, we see a really thick, heavy, dark brown smoke. And I want you to know that that brown smoke is an indicator of a wood product off-gassing. Now, the very first thing I want you to know is that does not necessarily mean that the structure is off-gassing. It just means a wood product is off-gassing. Things that are wood are furniture and a stack of old newspapers. So just because you see brown smoke doesn't mean the structure is off-gassing. It just means a wood product is off-gassing. But we can make a quantum leap here. Let's look at the garage again. Is that fire in the garage? Absolutely not. That fire is above the garage, more likely in the attic space. Now, what's typically associated with a structure or a wood product that's in an attic? Well, that's going to be the rafters and the actual trusses of the garage. In this case, what's supporting up the roof. What this is indicating is that you have a fire that's generating enough heat to start having the wood timbers inside the structure to start off-gassing. That's what brown smoke means. What about gray smoke? Take a look at this picture. You can see that this is a very large fire. It's in the garage, and you can tell this is a very intense fire, and the smoke is pushed very hard throughout the roof space and attic space of this structure. But I want you to look at the actual gray smoke, and I want you to start at the very top of the picture. And as you look at the smoke, I want you to move down to the eaves where the smoke is being vented. What is the difference in color between the smoke at the top of the picture and the smoke at the bottom of the eaves? The difference is that smoke has physically changed color. It's gone from very dark coming out of the structure, almost a dark brown or maybe even a light black. And then finally, once it's moved away from the structure and up in the air, the physical color has changed to a light gray smoke. What is that indicating to us? What do you think is happening? The reason the smoke is changing from a dark color to a light color is because it is incredibly hot, and it is a product that was created, in this case, in the attic space above the garage in an oxygen-low atmosphere. The second the smoke is pushed out from the attic space through the eave and into the atmosphere outside, it is now introduced to a new chemical that it's never seen before. That chemical is oxygen, and it literally starts to oxidize, and it is changing color because the compounds in the smoke, due to the high heat, are physically changing with the introduction of oxygen to the new mixture. The oxidation process is what causes that smoke to physically change color, and the only way that's possible is if it's very high heat inside the structure. This is an indicator now that we have a very well-developed fire, and it is very hot inside the structure. This gray smoke, this black smoke now venting out, used to be brown. So we now have an indicator of a fire that's in a full-out late stage growth phase, and it is very hot inside. Here's your curveball, yellow smoke. This is one of the best pictures I've ever found of this hostile fire event. What do you think is the potential scenario for this structure fire? The yellow smoke that we're looking at right here is one of the strongest indicators of a potential backdraft. Now, to truly understand how yellow smoke's an indicator of a backdraft, we have to understand where that yellow smoke came from. Yellow smoke is a strong indicator of a high hydrocarbon load. Again, we don't care what's the hydrocarbon because we know residential houses are filled with hundreds of different types of petroleum byproducts. That's the hydrocarbon. What we care about is how the smoke got the color. As the fire heats up, more off gases are generated, more smoke's released into the atmosphere of that house. And if it's not vented properly, that smoke, because it is so high pressure, is going to start being pushed through the walls and through whatever possible opening they can find. What ends up happening is that smoke starts to become filtered, and the actual carbon gets left behind, and the byproducts, the smaller molecular level sulfur, gets pushed out, giving us yellow smoke. This is why yellow smoke's a fantastic indicator of backdraft, because it's telling us that the fire is hot, there is a significant amount of smoke being released, and it's oxygen limited. That's why yellow smoke is a fantastic indicator of a potential backdraft. Once you see the yellow smoke, you're going to do your size up, your 360, and you're going to go back and you're going to evaluate the structure for your typical backdraft indicators. Are the walls bowing? Are the windows bowing? Is there any whistling noises associated with the structure? Is the smoke being forced out in unusual places? Are the windows completely sooted out? There's many others, but take strong note of smoke color and the potential of a hostile fire event. Black smoke is going to be an indicator of a fire that's in the late stage of growth, and it's going to be a hot fire. The reason the smoke is black is because the heat inside the structure is now physically starting to burn the smoke. The different fire gas layers inside the structure are starting to ignite, and the carbon particles are starting to be deposited in the atmosphere. It's also an indicator of just the particulates in the air, but it's also just a major indicator of the high heat load inside the structure and the fact that the different gas layers are starting to be consumed and carbon's now visible. Color will rarely tell us the material burning, and we don't want to try and assume the material burning off the color. We're using the color of the smoke to help us indicate what stage the fire's in. Again, white smoke is smoke that's traveling, but if it's a white, very very wispy, hard to see smoke. Well, that's a smoke from a very small fire. It's just started. There's not a ton of heat being left off in the building, and there's not a bunch of off gases being produced. So from a very small fire, even the distance is covered in a small building. By the time that smoke physically gets outside of the structure, it could be white in color. White is an indicator of either a fire traveling a long distance due to high heat and high pressure inside the structure, and it's pushing the smoke all the way across the structure, or an indicator of a small fire. Then when we get to brown, brown indicates that you have higher temperatures inside and that wood-based products have started to off-gas. And then when we get to gray, we officially know that we have high temperatures inside the structure and it's physically causing the smoke when it exits the structure to oxidize. And then we finally get to black when we know we have a late stage fire. It's starting to burn the separate fire gas layers throughout the structure, and we're starting to get carbon deposits as particulates leaving the structure with the smoke. And then finally yellow is just a gigantic heads up and a warning sign for potential backdraft situations. We're going to use color to help indicate the stages of heating, how hot it is inside the structure. We can use color to locate the fire. Again, white traveling smoke being pressurized really hard out of a structure is going to tell us the fire's on the other side of the structure. We've covered in great detail what color does for us. If you have any questions about these slides, please, by all means, have this discussion inside your home departments, and if you have any other further questions, bring them back here to the instructors. On a side note, there is going to be a quick discussion on black fire. Black fire is the term we give to high volume, high velocity, extremely dense black smoke. I want you to look at black fire is exactly like you would look at the flames themselves blowing out the windows right now. This is a good picture to show that the smoke leaving that structure at the second floor is pitch black. It's straight carbon coming out of that structure. And once it gets out of the structure, it still stays a very, very dark gray. And the real indicator on this is as it leaves the structure, the smoke's incredibly dense. It's still incredibly hot, and it's incredibly thick. There's a ton of volume to this physical smoke column. And black fire is the very last step right before you get to flashover. Now, in Texas, you're not going to see black fire all that often. And a lot of this goes back to building codes. At the end of the day, in our area, our buildings aren't built with true dimensional lumber. They're not built with screws and nails holding this wood together. And these structures with this type of heat inside of them in Texas, they will be compromised, they will start to collapse, and they will start to vent themselves. Black fire is typically associated with any structures in the Northeast or in the Midwest or the Great Lakes areas, and then also on any particular older structure. Black fire does occur in Hood County. I have seen it. It is rare. In the event that you see black fire, like I said, think of it as exactly like flames coming out the window, because that is exactly what it is. It's incredibly hot fire gases, and it is an impending sign of flashover, and it is not a fire to make an interior attack on. Other factors to take into consideration. The physical container. The most important factor, how is building constructing physically affecting your ability to fight this fire, and what is it doing with the smoke inside the structure? And lastly, weather. Weather has a huge factor on the ultimate outcome of your ability to do a competent fire attack on a structure. A couple of days ago, we had very high winds, sustained wind of like 15, 20 miles an hour with gusts into the 30, 35 mile per hour range. With wind that high, and you're never going to be able to fight a structure fire and save the structure. It's just not going to happen. Nature and physics and chemistry is going to overtake your abilities to fight that fire once it's well developed. Now, if you can get in there and you get it knocked down as a small early stage fire, then kudos to you and good work. But if you've got a well developed fire like any of these three pictures show, all wind's going to do is hurt you. Humidity. It is a major factor, and it can significantly help you. The moisture content of the air is going to restrict the fire's ability to grow. Now, it doesn't mean just because it's raining outside that you can't still have a structure fire. And don't ever forget that just because it's raining outside doesn't mean that you can't have a really advanced structure fire. But those are just two weather factors that we commonly encounter that do have significant factors when we're fighting structure fires and the effects that they have on the smoke inside a structure. Judge the change rate. Are smoke conditions getting better or worse? And this is something you're going to continually do as you're a firefighter making an interior attack or even preparing to make an interior attack. In between the time that you arrived on scene to the point at where you're ready to make entry in the front door, if that fire has exponentially grown and the smoke pushing out the door is so pressurized and so turbulent and now pitch black, is that the point at which we dive inside? After this entire slideshow, all I've said is beware black smoke, and here you are going in the front door when it's floor to ceiling and it's highly pressurized and it's hot as hell at the front door. If the conditions are getting worse, do not make an interior attack. Cool the atmosphere from the front door. See if that water burst inside the structure has physically changed the atmosphere enough for you to make an interior attack and progress inside. If it has, proceed with the interior attack. If it hasn't, continue to cool the atmosphere aggressively. With that said, as you make your interior attack, if you notice that conditions are getting worse, and one of the two ways you're truly going to notice that is the absolute decrease in visibility, and then the second one, and the really important one, is the crushing heat in the room. If you start feeling crushing heat in the room that's pushing you to the floor, what the hell's causing the heat? I can assure you it's not only the massive heat buildup in the room, but it's rollover, and it's all those separated gas layers that are igniting at different temperatures burning above you, and you're feeling the heat from the separated gas layers starting to burn. What's that an indicator of? Flashover. If you have indicators of rollover, you have got to aggressively cool the atmosphere for the room that you're in. If you continue to pursue your current course of action, I can guarantee you're about to have a bad day. You have got to make actions to physically take control of the scenario and the atmosphere that's about to blow up and kill you. If you notice conditionings are getting worse, be proactive, not reactive. Start cooling the atmosphere. And in worst case scenario, back out. It's okay to back out and figure out another plan of attack. That is just fine. Continue to cool the atmosphere as you back out. Now, if the conditions are getting better and you're doing good work with cooling the atmosphere, then by all means, proceed and go to the seat of the fire and extinguish the fire. But you need to be proactive in how you're anticipating what the environment's doing. Do not wait for an event to happen and then you try and react to it. Interpret the information that you're getting from visibility, interpret the information that you're getting from what you physically feel in the room, and then act accordingly. Predict the event. Consider one hostile event can and usually will lead to another event. So if you don't stop the fire in the growth phase, in early growth phase, the fire's gonna progress to just straight growth. And then if you don't stop it in the growth phase, it's gonna proceed to late stage growth. And at late stage growth, if you still can't stop the fire, then it's going to eventually move to our catastrophic event, a flashover. And if you can't stop flashover, well, then you're dead. You have to be able to realize what's happening around you so that you can take the necessary actions. Communicate your observations. While doing an interior attack, give lots of UCAN reports. Let incoming crews know that the fire conditions are getting worse. Let them know that the smoke conditions are getting better. Let them know that you've extinguished the fire. Let them know that you're backing out. Warning signs are not always visual. Use your knowledge and experience. Trust your instincts. I've got a great side story on this. 2011, we had the lodge fire here in Granbury. And at the lodge fire, this was a gigantic, gnarly fire. And here I am as a junior woodchuck firefighter, still brand new on Granbury. And here we are at my first truly serious, large structure fire. And I was with an incredibly experienced firefighter. This man had done firefighting for 30 plus years, and I knew that he knew what he was doing, whereas I was a complete bumbling idiot. We made entry on the 3rd floor of that fire, and as soon as we got in the door, we were immediately on our hands and knees trying to crawl in. What I experienced was visibility of absolutely zero. The only way we could see each other is if we put our face masks together. The heat was staggering. I have still not been in a structure fire as hot as that one. You could hear the fire absolutely roaring ahead of us somewhere. And then lastly, this feeling of this isn't good. That deep guttural feeling of dread. The firefighter, the experienced firefighter in front of me, and I assure you, we probably weren't 6 feet inside, he actually stopped and he turned back to me. This is when I could barely see each other and we were face mask to face mask. And he asked me, "What did your training tell you about this situation?" And I can't tell you what I told him back, but the moral of the story was, this isn't good and I really don't like this. And he said, "I agree. We need to back out." Here's the best part of this story. As we backed out, I happened to look over the handrail down to the 2nd and 1st floor. The other fire crews were backing out at the exact same point we were. You need to trust your instincts. There is nothing wrong with saying, "Holy crap, I do not know what to do here," or "This is scary, the hairs on my neck are standing up." That is your 6th instinct to back out. When you sense danger, back out, regroup, get the team back together. Trust your instincts. They will save your life. Other considerations or tricks. Watch open doors. Okay, and what we're going to be looking at is different smoke layers that we're seeing in a door. If the smoke to air ratio is 50-50 coming out that door, the fire's on the same level. If the smoke coming out the door doesn't lift out the door, in other words, it's just coming straight out and just kind of like a chimney, the fire's below you. If the smoke is stagnant or disappears above the door, the fire is above you, and it's going to be either in the attic or it's going to be on the second floor. Here are some basic shortcuts and not the absolute law of the land. If the smoke is very thick and very dense, and it's very dark in color, black, and it's moving very fast, this is going to equal a very hot and explosive smoke. If the smoke layer is thin, not very dense, still black in color, and moving very fast, that means the fire pushed is nearby. That means the fire is very close by. White smoke with speed equals a hot fire, but very distant. If the smoke is even in speed and color and from many different places, it's possibly a deep-seated fire. If you have brown smoke, it's unfinished wood being heated, and it's a potential collapse warning in lightweight construction. Lastly, very turbulent smoke flow, just really boiling, just really getting it, potential flashover. Test time. Yeah. All right, guys, take a look at this structure. I want you to tell me a couple of things about this structure. I want to know how big the structure is. I want to know what the structure is made from. I want to know the approximate age of the structure. And I want you to tell me a story that smoke is telling you. Same thing. I want you to tell me a story about this structure. What type of structure is this? What is this structure used for? What type of construction is this structure made from? Is there anything special that we need to know about the material that's on the outside of the structure? And then lastly, tell me the story about the fire and the smoke that you see in this picture. This picture, there's a lot going on here, and there's a very sad story attached to it. If you notice the ladder that's kind of behind a tree in the middle of the picture that goes up to the second story window on the right side of the house, a firefighter made entry into the structure at that window. Tell me a story about the smoke, the intensity of the fire that the firefighter encountered, and then also tell me about this structure. What type of structure is this? What is it made from? And what is our potential hazards with this structure? Tell me, what is the difference between the two smoke pictures here? There's something very specific going on in each picture. Tell me the difference. You guys need to figure out how to do this, because this is going to be your job when you ride out on a truck. You need to be able to figure out how to do these interior fire attacks. Tell me, what is the difference between the two smoke pictures here? There's something very specific going on in each picture. Tell me the difference. You guys need to figure out how to do this, because this is going to be your job when you ride out on a truck. You need to be able to figure out how to do these interior fire attacks. I want to personally thank each and every one of you for the time, energy, and effort that you've taken out of your personal lives, not only to help your community, but to also dedicate to just going through our Simple Fire Academy. The benefits that you're going to make every day in someone's life are immeasurable. And it's not always the big stuff that makes the difference. And please keep that in mind as you experience and grow on your home fire departments. There's a lot to learn outside of our fire academy. Be energetic on your departments. Be involved. Go to these extra training classes that are provided throughout the state. Talk to every single person that you can when you have a chance about fire-related material. You talk to another firefighter, and chances are they're not going to shut up either. And you're going to be able to figure out a lot from just working with each other. Always, always, always take time to talk to your old crusty guys on the department. Like it or not, they've been around the block. They've been to these fires before, and they are a wealth of knowledge and experience. They're going to give you the footing that you need on a scene. They're going to be the steady hand in the dark that's going to take you to the seat of these fires and extinguish them. Please work with each other. Communicate with each other. This is effective teamwork here, and it's done at the station. It's practiced on scene, but the true communication's done at the station. The true learning's done at the station. Take every opportunity that you have and train. You'll never be prepared enough for the million different types of situations that we'll encounter. Lastly, I would love to know what you think of this online fire academy, and it is absolutely critical that we get feedback on it. Is it too much? Is it too little? Do we need better materials? Please take the time to review the class, and please take the time to actually let us know what needs to be improved and what was really good for these classes. It's the only way that we can make the program better. Now, at the beginning of this slide, I didn't introduce myself. This will be the last time that you hear from me, Captain of Operations Matt Hohan, here at Granbury. And the last thing that I want to leave you with is always take the opportunity to talk to the newest members on your department. Build those relationships early. They'll carry you through the rest of your career.